freigegeben wird. Hello and welcome to my presentation about Rowhammer and the countermeasures against it, specifically based on Can't Touch This. Who am I? My name is Niklas Deidert and I'm a student of Angewandte Informatik or Applied Computer Science at the University of Applied Sciences in Flensburg. The topic of my presentation is Rowhammer. It's a security attack based on DRAM exploitation and the countermeasures against it, specifically based on the Can't Touch This research paper. Okay, let's cover the background you need to understand this attack and a countermeasure. The DRAM, Dynamic Random Access Memory, is an integrated circuit containing a capacitor and a transistor. So, a capacitor is a device used to store electrical energy in an electrical field. So basically, you can store, it can be filled or it can be empty, which is representing the two values of a bit. Charged equals 1 and discharged equals 0. And secondly, we have a transistor, which amplifies or switches the electronic signals and uses a small signal current to switch to a larger one. So you can load the capacitor or unload the capacitor through the transistor. Okay, so DRAM. One single cell is this circuit with a capacitor and a transistor. Multiple cells build one of these rows. See, row 4, row 3, row 2, row 1, row 0. Multiple rows build a bank, which is this whole grid with all the rows, and every row has a row buffer. That's the basic structure of your DRAM, and you combine multiple banks to form a big block. And on your hardware RAM stick, there are many of these blocks. Okay, so to read and write on your DRAM, you open the row by transferring the data from it into the buffer by the process of which the reading process into the buffer empties the capacitor, and then you have your data in the capacitor. And when you write back the row from the buffer to the capacitor, you load it again. So you switch. You swap between loaded and unloaded state multiple times. Okay, now the attack theory. The theory: assume a cell in the victim row holds the value of having admin privileges or kernel privileges. It's probably set to 0 because your application isn't allowed to affect the kernel. So this data is stored somewhere in this victim row. The attacker rows are either one or two of these rows surround physically next to the victim row is what you need to target for the attack. You achieve this usually by, for the attacker row, you just allocate huge amounts of memory and hope that you hit this space. The same really for the victim row. You try to allocate it somewhere in here. Somewhere in this victim row. Okay, assume the attacker finds one or both of the rows adjacent to a victim row. So he will allocate a big space and checks if anything, if it is adjacent physically on the cell next to this victim row. And then now the attacker starts hammering the row, and he repeatedly opens, reads, so he discharges the capacitors, he refreshes, he charges the capacitors again, and he repeats this. So it's high, low, high, low, high, low, which is generating electric field or an electric field which generates a magnetic field which influences electric fields that are adjacent. So by switching the values in the aggressor rows on and off and on and off and on and off and on and off. At some point, you have a chance to flip the bits from 0 to 1 in the victim row. So at some point, you suddenly have root privileges or admin privileges. Here, the hammered row starts building electric field. This is the Maxwell equation if you want to find out more about it. Okay, the attack in practice. We are looking at a code snippet by which you can repeatedly flip the switches in your X and Y, which is we assume this is X, for example, and this is Y row, this is Y, this is X. So this is the start of the code. You declare a block of code. Move X, so you're moving the data from X into the buffer. You're moving the data from Y into the buffer, and you store it in the buffer in the cache. The next thing you do is you just clear it again because you don't really want to do anything with it. So you write it back into the row, and so you have achieved unloading and loading again. And now you make sure the cache was completely flushed, just to make sure that you can repeat the process without problem. And then you jump to the start of the code 1A block, which is up here, and repeat this up to 10 to the power of 6 times or more. Just flip back and forth in your aggressor rows, and at some point the electrical field will build up enough to flip in the adjacent row. To increase the effectivity of Rowhammer attacks, or rather gaining access to the correct aggressor and victim rows, allocating huge amounts of memory and repeatedly doing that works for the aggressor rows. And for the victim row, you try to make the operating system create multiple copies of the victim data and try to store them in as many places as possible until you make it copy a version of it in the victim row that you have identified as a vulnerable place for Rowhammer attacks. Okay, now let's talk about countermeasures, specifically from the paper. Okay, this is the hardware approach. No, we're talking about generic countermeasures first. Hardware-based approach, it leaves existing hardware vulnerable. So if the hardware designers suddenly decided they wanted to change something that prevented or hindered this electrical buildup or the Maxwell equation electrical buildup, that would leave all hardware that has been produced up to date still vulnerable. So it wouldn't help any existing system really. Another is a heuristic-based software approach, which sadly suffers from false positives. So it some processes, some applications just do stuff that looks like a Rowhammer attack and might be hindered by that. And also it has a memory case overhead, which just slows down your total system. Okay, now let's talk specifically about Can't Touch This, practical and generic software-only defenses against Rowhammer attacks research paper. Okay, this is published by 5 people, Ferdinand, David Gens, Christopher Liebchen, and Ahmad-Reza Sadeghi from CySec, Technische Universität Darmstadt, and Lukas Davi from the University of Duisburg-Essen. Okay, the goal is to create the first practical and generic software-based defense, so nothing with the hardware, so it can be applied to legacy systems, which is a goal to protect these. And there should be no or as low as possible performance overhead and no false positives. Okay, this whole countermeasure is split up into 2 parts. One is BCAT, which is supposed to mitigate malicious bit flips. It does that by extending the bootloader right when your computer is starting up, or if your computer is starting up, and the memory is allocated. So the memory is allocated, and then the BCAT makes the bootloader also uh, also it names some memory as unavailable, and this memory is scanned. So the memory is scanned to identify multiple memory pages, and this BCAT makes these unavailable for the operating system, so no one can touch this. The problem with this is that there have been research papers that show that temperature and aging and different things may change what is vulnerable and what isn't. So this is not a surefire approach against a changing system. It is at a snapshot at the moment where it is scanned. It is very, very effective. Here we see a graphic. So we have an offline analysis. We locate the vulnerable memory in our memory DRAM. This address, for example, yeah, that could be bit flipped maybe, and this could be bit flipped. So we create a blacklist, and this is given to the bootloader. So the memory is allocated, and then to additionally, there's these parts of the memory that are also allocated but are listed as unavailable. So no access, no changing these. Here you can see another graphic where this is better shown. So the Linux kernel sends the boot script to the grub2 bootloader, which from the BIOS, which was started from the BIOS. It gets the E820 map, which is just this this list. These are address ranges, they are available, these are reserved, these are available. So it gives these back to the bootloader. The bootloader then gets a message from BCAT that's saying, okay, please add these from my blacklist as well to the list. So we have this block that's vulnerable, that's reserved, this block's reserved, this block's reserved, and then we pass this back to the kernel so the system can do whatever it wants with it. Okay, the second part of the can touch this software approach is GCAT, which is generic approach. So it tackles the malicious effect of bit flips by extending the physical memory allocator of the OS. So it changes how the memory allocation works on your system. It limits bit flips to memory pages that are already in the address space of the malicious application. Okay, this means you have a little block of code that's from your application, and then you have an isolation. In isolation from that is your code from your system, from your kernel. And you physically can't cross over this distance with the electric fields. Here we can see this is the physical memory. This is security domain A. This is some user mode application. This is whatever, some program running over here. Here is a security zone, basically. There's nothing in here. And here, in this checkered part, there's kernel mode memory. But since this row is empty and this row is empty, you can't flip these from outside. So they did some testing, the authors of this paper, and they did a lot of Rowhammer approaches firstly on just unprotected systems. They had 3 systems with similar physical makeups, and with no protections, they had a lot of Rowhammer effects. With BCAT, they had no effects. This is vulnerabilities. This one is vulnerabilities. So they found a lot of vulnerabilities with this, but with this, where they blacklisted the vulnerable parts from the memory through the bootloader. This is BCAT. They found no vulnerabilities. And now they try to just use Rowhammer exploits on the system with no protection. They managed it in average 11, 42, 53 tries. And with BCAT and GCAT, they tried to run this tool that does Rowhammer attacks on the system for like 2 days or more, and just didn't get a successful Rowhammer attack. So it was pretty effective on the systems they tested it on. They also tried to they also measured the performance impact. The performance overhead generated by BCAT or GCAT was negligible. The differences were mostly probably based on measuring errors from the testing suits they tried. Basically in the 2% positive negative range. And the memory overhead is very small because there's just one row in every memory bank that's off limits through this physical separation that GCAT does. So the memory overload is about 2 to the power of 15 or 0.0 something. 0.03. So you can see here 0.0631511. So there's not a lot of impact on your system by running this. Okay. Generally, the BCAT is able to protect all Linux-based systems, OpenBSD and Xen. And at the time of writing the paper, you couldn't really do it with Windows or UEFI because it works with grub2, and that can't hand over this blacklist table to the Windows bootloader or UEFI. UEFI is not a problem as far as I read, but Windows would need the Windows creator, Windows developers to help with the process of integrating this. And GCAT can be used on any x68 or ARM systems, which is mobile devices mostly, with some changes to the kernel. So this could be implemented very easily by the developers of these systems. But as far as I know, it isn't really. Okay, now in comparison to approaches that we have discussed, which is the hardware-based approach that the developers need to change something physically on their DRAM sticks, and the heuristic software approaches, which produced so much overhead and false negatives. So positive, this one has no really performance impact, and it is hardware independent, really. So it's not dependent on the DRAM stick or whatever. It's dependent on the bootloader, which is the negative part. So as I said, it doesn't work with Windows. It didn't work with Windows. I don't think they talked about Apple. I'm not sure how that works there. Yeah. So that's really it. So it works very well, but it just isn't really implemented in real life yet. Okay, in conclusion, Rowhammer is a very dangerous exploit, and there's really nothing, as far as I know, that has been done effectively to stop it. You can, by attacking the hardware, just totally ignore the software, whatever is running on there, and get access to whatever you want if you're lucky and if you have time and patience. A smaller DRAM stick would make this even easier, and smaller is better because more performance can be put on the same size of stick. So the danger would increase because the electric fields wouldn't have so much space between rows to impact the adjacent ones. Effective countermeasures against all known Rowhammer attacks. At the moment of writing, there's only this is an effective countermeasure. This can't touch this research paper. It's software-based, thus effective for hardware, legacy hardware, and physical and software-based separation of vulnerable memory. So you can't actually impact the vulnerable parts that you try to impact indirectly. So it is effective. It's just not implemented. Okay, my sources are mostly the reading assignment, this research paper, and the course. Thank you for listening.